All right, let's go ahead and get started. Before I do, if you want your copy of exam number 2 back, just hang out and I'll give it to you after class. I have them. I also have a lot of exam 1, so I don't want to assume that everyone is really desperate to have them back. But if you want it, I have it for you. All right, so we talked about optimization last time. Got a couple more examples to go through. This is one of those areas of calculus that it's a really, really important application, derivatives. Unfortunately, the problems have a lot of different looks. I can't really give you like a bulletproof process to always follow, but hopefully after we look at a few of these, you'll see some commonalities and get used to organizing these things in a helpful way for you. So I want to find the point on this parabola that is closest to that point 5,3. So what would you like to do to get started?
Set the equation equal to 5.
So what equation equal to 5?
The equation equal to y. X plus 1 squared.
Y equal to 5.
Because no. So that would give you the x value that gets you to 5.
Why do I want y to equal 5?
No, you want y equal to 3, don't you?
Okay, that's why I was asking why you set it equal to 5. Is the point 5,3 on that parabola? No. So if it was, this would be really easy because the closest distance would be 0. So that point 5,3 is not on that parabola, but there is some point on that parabola that is nearer to 5,3 than any other point. So that's kind of the objective here. Anything else we can do to get started organizing this? What have we done previously?
Find the derivative.
Okay, I heard draw it, I heard find the derivative. Certainly draw this. Do we happen to know what this parabola looks like?
As quadratic.
So yeah, I mean, it has a parabola shape, which we know what it looks like.
1 over to the left.
Yeah, that's the. So again, it can look bad. I'm just trying to organize myself. So I got my parabola. That's my y equals x plus 1 squared. Anything else I should put up there? Yeah, I think that point is somewhere to the right of this. So that point 5,3. And I'm trying to find, yeah, there's some point on that parabola that's closer to 5,3 than any other points on that parabola. So this is kind of what I got going on. I heard take a derivative. We want to go take a derivative. Has taking a derivative been valuable in other ones? Do we have the thing that we need a derivative of yet? That I'm not convinced of. Isabel?
Could we take the limit of the function as it approaches 5, as x approaches 5?
What will that do?
I mean, I think it would trace the function up until whatever point is closest to 5.
Okay. So this is a polynomial, right? So that limit will just be equal to whatever y is when I plug in 5. So that'll be 26. So when x equals 5, y is equal to 26 on the parabola, right? So here's something we found. I found that I can find a point whose distance is 23. So if I can beat, hopefully I can beat that. Otherwise, that's our closest point. Do I know that's my closest point? Can't say that yet. So I'm trying to find the closest point. So if we look back to, maybe I'll flip back to our last example, just to kind of refresh how we were looking at these things. So we drew a picture. That's awesome. What are some of the other very early things we did? to organize what we were after. Isabel?
We looked down the functions that were related.
Okay. So specifically, I mean, two big things that are going to crop up in all these. You have something you're trying to optimize. And then on top of that, you have something that's going to restrict it. So what is, in this case, what am I trying to optimize? Like, what's my goal?
Distance. Sorry.
No, you're fine. Are we finding a maximum distance, minimum distance? Okay, so we're trying to minimize distance, right? And I think so far with all of these, we're trying to either maximize or minimize something, right? So maximize the distance between what things?
Between y and the point.
I'm going to say between the parabola and the point, because I don't want it to look like we're only looking for the y values. Between the parabola and the point. So we're trying to optimize that, right? What's our restriction? Do we have any restrictions? Parabola itself, right? Are there any other kind of restrictions we need to worry about? I think we have to take into account two things, right? Let's say, even though this is, let's say this point right here is the point we care about. That's the point that's closest to 5,3. So I'm going to call that thing, just for now, XY. So I'm trying to minimize distance, right? Can I represent that distance mathematically somehow? Trying to find the distance, basically trying to find the distance between 2 points, one of which is unknown, one of which is known. Pythagorean theorem, does that sound good? So in reality, yeah, I have the distance between 2 points in two-dimensional space, so I can think of this as a right triangle. So yeah, let's model this off of this. A squared plus b squared equals c squared. I mean, that's Pythagorean theorem. Can we get a little more specific about things? How many variables am I looking at with that equation? That's 3, right? That's a little too unwieldy. So can I simplify this a little bit? How many variables can I really deal with? 2. I have an independent variable and the dependent variable. So I need to somehow get this thing down to 2. So what are the A, B, and C up there represent? Okay.
Did you put x squared plus y squared equals d squared?
Let's talk about that. X squared plus y squared equals d squared. Okay. In your mind, what do x and y represent?
Isn't y already a function of x? Can't you just sub it in for y?
Oh, hold that thought. We will do something like that, but I don't. X squared plus y squared equals d squared is a fantastic next step. We got to modify it a little bit. Why do we have to modify it a little bit?
Because it's just we need to get like the distance between. Because there's still 3 variables there.
Right, so that's part of it. And I think what Solomon is saying will clear that up for us, but we still have a little bit of work to do. So I labeled this triangle up here, X and Y, on the horizontal and vertical sides. I labeled this horizontal side X. Is that distance between, like the way I've drawn that distance, that's the horizontal distance from the parabola to the point. Is that really just whatever the X value is equal to? It's the difference between whatever that X value is and some other X value, right? What's the other X value? 5, right? So I want to know how far apart X and 5 are. So because of that, I'm going to rewrite this as X minus 5 squared. Similarly, what is Y? Or what do I have to do? What do I have to modify that Y squared bit with? Y minus 3. So yeah, if I was trying to find the distance from that parabola to the origin, then I could just leave it x and y, right? But I'm really looking for how far away that my parabola is from this 0.53. So now I like this equation. I believe this is true. How many variables are in it? 3. Solomon had a good plan to get this thing down to 2. So we'll make that change. So now we can do this. D squared equals x minus 5 squared plus x plus 1 squared minus 3 squared. We happy with that? Okay, so now I have an equation that is, it's a function in 2 variables, right? So now that I have, go ahead, Solomon.
So the point that we want to figure out is x, y, like the top left.
Yeah, we're trying to pin down where that is.
Okay.
And again, just to remind, like, kind of the whole point of why I'm doing this, or why we're doing this. How am I trying to find x, y? What's special about x, y?
It's the minimum distance.
It's the closest to 5-3. So that's why this equation exists, because this deals with distance. So now that I have that equation, that function for d in terms of x, what do I do with it?
Take the derivative.
Why do I take a derivative?
Because we're trying to find the minimum.
I'm trying to find the minimum, and how do I find a minimum of a function?
You find where the derivative is 0.
Right. So if I want to find where the derivative is equal to 0, I need to find the derivative. So what am I going to take the derivative of this thing with respect to what variable?
X.
Right. So, and this time I have a little bit of a implicit differentiation situation going on. What's the derivative of the left-hand side going to be with respect to x? That t squared.
2d dx.
2d dx.
Would you have to do implicit differentiation, or could you just like?
I think the other obvious alternative is to square root both sides,
Yeah.
but then that derivative,
It's pretty gross.
I don't want to do it.
All right.
Yeah, so yes, there's an option. I don't know if it's preferable. All right, so right-hand side, how's this derivative going to look? I believe this one's just 2 times x minus 5. And this one's going to be a little more complicated. 2 times x plus 1 squared minus 3 times the derivative of the inside, which is going to be 2x. I did that one pretty fast. So I'm going to pause because I'm looking for bugs in it, just like I think you all should be. I'm not totally convinced. So what I believe, so I'm happy with this one. This one over here, so 2 times this whole thing raised to the first power, right?
Yes.
Times the derivative of this inside part, which would be 2 times x plus 1, which I don't have. Oof.
Can the distance between any 2 points be represented by a right triangle?
In 2 dimensions, yeah, absolutely. Okay, now I feel happy about it. I'm glad we let you do that. All right, so, and I want this thing to equal 0, right? Anybody mind if I just divide this whole thing by 2? Is there any possible way that the distance could be 0? Our distance d? No, why not?
Because the distance can't, like, for context, the distance can't be zero.
Well, sometimes it can be, but why do I know in this case it can't be? Because
It's not on.
yeah, there you go. Yeah, that point that I care about is not on that parabola. So the distance is always positive, which means I can divide both sides by d. What's 0 divided by d? Still 0. So that d kind of cancels out. So now what I have is this. D dx equals x minus 5 plus 2x plus 2 times x plus 1 squared minus 3 equals 0. Any questions so far about where we are? I see some dirty looks though, and I think I understand why. So yeah, I mean, right now I think the algebra ahead of us is a little bit, it's going to might get a little hairy, but what I want to focus on is, do we understand how we got here? And also importantly, do we understand where we need to go to finish this off?
So just real quick,
Go for it.
so the D, you just divided.
Yeah, so that's why I was asking if it was possible for the distance to be 0. And since it's not, then I can divide by it.
Okay, but then you would only divide, like the 2 equal signs things kind of trick me out. If you divide everything, so yeah, I get that part, but then what about the middle part?
I mean,
Do you divide everything by D, or is it just like?
the real convenient thing here is that I'm dividing 0 by stuff, right? So let's say that, okay, yeah, it's probably a good practice for me to divide all this middle stuff by 2D. I still want this equation to equal 0, right? I have something divided by something equals 0. The only way that can happen is if the numerator equals 0. So I took some liberties and probably didn't explain all the shortcuts I was taking.
Yeah.
Cool. All right. Are we okay with this? What do I do with that thing?
Solve for X.
We can't solve for x, but I'm wondering if it's just a better use of our time if I just give you the answer. And
Well, yeah, because like we know at least one of the zeros is 5. So
no, you don't.
we don't.
Mm-mm.
Is there addition though?
It's under addition. So the derivative. So yes, if x is equal to 5, that first one will be equal to 0.
Yeah.
But you're going to be adding to something that's not 0. If they were multiplied together, I absolutely do. But the fact that I'm adding them.
Oh yeah, you're right.
Right.
So,
Here's what I'm gonna do, because there's one more example I really want to look at. I'm going to. No, let's finish it. That's cheap. So to solve this, I really need to expand all this stuff out and hope it simplifies in a way that I can deal with it. X plus 1 squared will be x squared plus 2x plus 1 minus 3 is minus 2. Let me know if you see anything that looks strange up here, because I'm trying to rush through it a little bit. Okay, so I got a cubic and I'm not quite sure how to deal with it. So I could go to a graph and do this. Here's one thing I want to point out, and I should have recognized a lot earlier. So here's what we're doing. Something I recognized a while ago. I'll post the solution to this so we can move on. But here we substituted this thing in for y, right? I think what would have been easier to do is to substitute the other way. And I'll briefly show what that looks like. So hopefully it makes sense, but. So this is all based on Pythagorean theorem that x minus 5 squared plus y minus 3 squared equals d squared. Instead of substituting, writing this equation in terms of x, I want to write it in terms of y. So I'm going to keep the y minus 3 squared. But what can I do for x minus 5 squared? Is this true? Y equals x plus 1. Actually, I don't know if that's going to work any better. Yeah, give me some time to think about this. I'm losing the plot of this one right now. Let's move on to the last one. So I got a picture. So we're starting from point A. We want to get to point B as fast as possible. And we're given a speed that he can row a boat and a speed at which he can run. So basically he's gonna row his boat from A to B, dock it, and then run down to B. All right, so what am I, let's figure out our goal first. What am I trying to do?
Maximizing his speed.
So I don't think it's maximizing speed. Because if I really wanted maximum speed, what would I do? I would spend the most time that I could running, right? But that's not really the objective. It seems kind of counterintuitive, but it's not really speed that I'm trying to optimize. What is the thing that I'm trying to optimize? I'm trying to, no, shortest path, not really either, because. So what would the shortest path be here? Straight line between what two places? A and B. So straight line between A and B is the shortest distance, right? But what does he do? What does he do faster, row or run?
Shortest distance according to the different speeds. Combining the two, like you can run faster.
So you're saying shortest distance with respect to speed.
Yeah.
I can combine that. So basically, shortest distance. So you're looking for the ratio of distance to speed. There's a simpler way to say that. We're looking to minimize this time, right? So and all those things, I mean, it feels intuitive, like I want to go as fast as I can. But to give you an extreme example, if you go really fast the wrong direction, it doesn't help you. So it's not really speed that I'm trying to maximize, it's time that I'm trying to minimize. And maybe the minimum time is not going to come from the fastest speed. Because is the distance in here going to be constant? No. So depending on where he lands, so like we have some negotiability on that point D. So A, B, and C are all fixed points. What we're really trying to figure out is where should D be? Okay. So our goal is to minimize travel time. And what are we constrained by? Yeah, so basically he has distance to cover and you can't move at infinite speed. So that's kind of the restriction we're working in. So we're trying to minimize travel time. Can we come up with an equation for that time?
X is speed equals what, like 6x 8y.
6x. I'm hearing X and Y, so that says we should probably talk about what our variables are before we start assuming that we're all on the same page. So what are our variables here? Row and run, right? So how far he rows and how far he runs. And aren't both those things going to be connected by this, by wherever I place that point, wherever I decide to land the boat? So really what we're looking at is, I'm going to say this is our variable. I'm going to call this X, because that's basically what we're doing. How far downstream am I going to land? So he's going to do two things, right? So I'll write my equation like this. Time is equal to time rowing plus time running. How would I find the time he spends rowing? Does he row at a constant speed? Okay. So if I have a constant speed, do I know what the distance is that he's going to row? What would that distance be?
6 kilometers.
That is speed. So remember, our distance is not constant. Our distance is a variable thing. So he's going to row from A to D, right? If he rows from A to D, so let's write this another way. It's equal to the distance rowing divided by 6 plus the distance running divided by 8. We agree with that? And X is the name that I've given to that variable for basically how far south of C am I going to land the boat. So if I'm landing X kilometers south of C, am I rowing X kilometers? Like how far am I rowing? You need Pythagorean theorem, right? So he's rowing on a diagonal line. So Pythagorean theorem. So it's what over 6? What's the rest of this expression? We know that the vertical leg of that right triangle is X. What's the horizontal leg of that right triangle? 3. That's a constant 3, right? That's the river has a constant width. So this distance is going to be the square root of X squared plus 3 squared. Any questions about that? It's not obvious at all where that comes from. So again, I mean, they kind of labeled it up here, but I'll make it more obvious with my own labels that this distance is 3. This one's X, so this one here has to be the square root of X squared plus 3 squared. What is the distance he's going to spend running? Or what's the distance he's going to run based on that X value? 8 minus X over 8. We okay there?
Pythagorean theorem, right?
What's that?
Not all of them, Pythagorean theorem.
Not all of it. Only the first half. So you basically, the 3 points it's going to hit in order are A, D, and B, right? So yeah, the distance from A to D, that is Pythagorean theorem. The distance from D to B, the whole distance is 8 kilometers, right? So since I called X that top distance, the bottom distance is just what's left. So this right here is my function of time, right? really want to minimize this. So how do I minimize it? I'm trying to find the minimum of a function.
Yeah, so you gotta take the derivative.
I need a derivative. So I'll call this, yeah, dt over dx, which probably looks a little weird, but it's okay. First term is the hardest to deal with. So 1/6 times 1/2 times x squared plus 9 to the negative 1/2 times 2x. And then minus 1/8, right?
Those two terms right there, the 1/6 squared root x squared plus 9, is that just by like dividing?
Yeah, instead of having this divided by 6, we just multiply by 1/6. And then what in here simplifies? Anything? So 1/12 times the square root of x squared plus 9. All right, so from here, what do we do? So I'm going to go ahead and cross multiply. So I'll get 8x equals 6 times radical x squared plus 9. Really don't like having to deal with the radicals, so I'll square both sides. 64x squared equals 36 times x squared plus 9. 28x squared equals 36 times 9, which is 324. Yeah. So from here, we should be able to find an x value, right? So x squared equals 324 over 28, which is equal to 81 over 7. So final answer in our margin here will be x equals 9 over the square root of 7. Or is that our final answer? Did I actually find the thing that I was asking about in the first place? Yeah, how far downstream should I land the boat? I think that's what x was representing the whole time, right? Okay, so let me leave this up for a bit. Let's take some questions. This is the last example I wanted to go over with optimization before I moved on, but plenty of time to talk about whatever. So we've done 4 or 5 of these. How have we started most of them, if not all of them? Yeah, so yeah, and I recommend writing it down, that you're actually writing down what you're trying to figure out. What else do you need to know beyond just like, what are you trying to figure out? What's that?
Figure out the variables.
Figuring out your variables. Let me ask a guiding question here. If my goal was to minimize travel time, I would just not move. So that's not acceptable. So what else do we have to think about? What are you required to do? In this case, I'm required to get to a place. So that's going to factor into you optimizing this. You have to meet some kind of condition. Figuring out what the variables you're going to use are. This might be the first time we got away with a single variable right off the bat, but I think that's the only time we got away with that. Figured out variables. Once we figure those out, what do we do? got an equation. Is that equation related to our goal that we came up with in the beginning? It better be. Otherwise, your equation is not the one you really want. So we were trying to minimize our travel time. We found an equation for time. Those two things need to be in pretty close agreement. Once we found that equation, what do?
Take the derivative to find the minimum max based
Right.
on what the thing is asking.
So yeah, first thing, take a derivative, but most importantly, you're taking a derivative because you're looking for extreme points. You're looking for minimums or maximums. Then once you have that, you should have everything you need to figure out like the whatever value of whatever variable you're dealing with will get you there. So I'm going to open up, or I'm going to set a due date for this this web work. I'm probably going to put I'm probably going to make it due by Thursday at the very earliest, but hopefully you're seeing these are kind of complicated. I would not sit on these until Wednesday night. Also, from if my past experience has taught anything, you probably can't do this without asking questions or getting help. So look at it early, come to office hours, send me emails, asking questions about it. But yeah, don't wait on this one. Anything else before we move on?
And don't be afraid to draw pictures. Actually.
Don't be afraid to draw pictures. I have never drawn a good picture for any of you in here. I never will. It's about something called antiderivatives. And this is kind of getting us set up for an idea that you'll spend most of Calc 2 dealing with.
It's the hardest part.
I am not the right person to ask. For a couple of reasons. Number one, it's been 20 years since I've taken the 3 Calc classes. And the things that I remember being hard for me were not, when I taught high school, I kind of warned people, oh, Calc of this is the hardest. And then 2 years later, I had students come back, you're wrong. It's not that way. So here's the good news about math. It always gets harder. You're always getting better at it too. So it is not good for me or any of you if I say you're ready to go to Calc 2 and you're not. So I know that's not the answer you wanted, but that's as far as I feel comfortable going with. So we're going antiderivatives. The prefix anti implies exactly what we're trying to get out of these. Instead of asking you for the derivative of a function, I'm giving you a function. You tell me a function whose derivative is that. So give me a function whose derivative is 4.
Any number for
No, not any number.
any.
4x sounds good. Is that the only answer you could have?
No, 2x squared.
I don't believe 2x squared. I believe 2x squared's second derivative is 4. But is 4x the only function whose derivative is 4?
Yes.
So this is kind of a weird thing about going the opposite direction. Lots of antiderivatives. Infinite amount. How about g of x? Give me a function whose antiderivative, or sorry, give me a function whose derivative is 10x.
5x
Squared plus what?
plus 3, 4, 8.
Cool. I thought I heard plus x, which I had a disagreement about. How about a function whose derivative is x squared?
One half x equals. No.
Let's think about it this way.
1/3 x cubed.
1/3 x cubed plus pi to the e. So if I ask for the derivative of x squared, what would you do? Like in English, in words, how would you do that derivative?
Exponent minus 1.
So you multiply, you take the exponent, you multiply it by it, right? And then you subtract the exponent. Antiderivative is the opposite kind of thing, right? So you do the opposite steps in the opposite order. You add 1 to the exponent, then you divide by whatever the exponent is. Which is basically what this is, right? So basically we're taking all the derivative rules that we've done and now you're kind of, it's an inverse. You're redesignating the direction in which you're doing it. So a function capital F is called an antiderivative on F on some interval if this thing is true. If capital F prime of X is equal to lowercase f of X. Capital F prime of X is equal to F of X. So just like when I use the prime, when I put a prime next to a function, it has a very specific meaning about how it's related to some other function, right? Capital letters are kind of the same way. If I call a function capital F, it is the antiderivative of something specific. The fact that it's a capital letter implies it is the antiderivative of. Isabel?
Does that apply to any time that we saw capital F in various chapters?
I mean, I guess it could, except is there a second function that corresponds with it that you're given?
I thought I had to look at it.
Yeah. If there is, then yes, but probably just for the author to avoid using lowercase f for every single function.
Okay.
That's my guess. So theorem, if capital F is an antiderivative of f on some interval, then the most general antiderivative of f is this. And I just showed it to you, basically. First thing I asked you was, give me a function whose derivative is 4. And in just a couple of seconds, you realize that you could give me an infinite number of things, so that was true. So to capture all of those, we say that the antiderivative of lowercase f is this thing, capital F of X plus C. C stands for an unknown constant. Because it's called an arbitrary constant of integration. When you're doing this in the inverse direction, there's no way of knowing if a constant existed there. So we just put that generic C there to show that it might have existed. If capital F prime of X and capital G prime of X. So basically capital F and capital G are both antiderivatives of F. What can you say about how capital F and capital G are related? Could they be the same thing? They could be the same thing. Must they be the same thing? Give me an example. Let's say f of X is 2x. Can you give me some f of X and g of X that are? Yeah, the capital F and G have to be different. Or sorry, do they have to be the same?
Two functions have the same. How can a function have two antiderivatives?
It definitely could. We're about to show you. So 2x is the function. What is an antiderivative that it could have?
X squared.
Are there others?
Oh,
So that's how a function could have many antiderivatives. Unless I give you more information, you cannot say for certain that either one of these two things is the antiderivative, or if it's something completely different. That'll be more clear when I actually do give you information we can find what that missing C value is. But for right now, when you're doing an antiderivative, basically it's going to be in this general form. Some function plus a constant. So let's find the general antiderivative for all these things. So power rule, basically. You have some variable x raised to the power of n. I don't want the derivative though, I want the antiderivative. And one thing we said was, all right, I'm going to take a derivative of x to the n. It's kind of a two-step process in a way. What's that first step you have to take when you take a derivative?
n times x n minus 1.
So first you multiply by n, and then you subtract n by 1. So now you're going to do those two steps in the opposite direction and doing the exact opposite thing. That's kind of what an inverse function does. So instead of subtracting n by 1, what are you going to do? Add n to 1. So this antiderivative is going to be x to the n plus 1. Then after I do that, what am I going to do? Divide by n. N plus 1. Yeah, not n. Because the exponent is no longer n, it's n plus 1. Is that the full derivative? Yeah, or full antiderivative? Plus c. Let's say we're not convinced. Can I take a derivative of this capital F thing? What's the derivative of x to the n plus 1 times n plus 1? So you've been doing power rule for a while now. So we're going to multiply by that exponent, right? N plus 1. We're going to multiply that by x to the n plus 1 minus 1. And the whole thing was originally divided by n plus 1, right? So that cancels that. That cancels that. So go ahead, and that's something I really recommend you all do while you're getting used to going in this direction. Is if you have any doubt, just unwind the process and make sure you get where you start. All right, so put a caveat here. This only works with the power rule as long as n is anything but 1. Should not be 1. That should be n equals -1. So because this acts differently. Because g of x equals 1 over x, that's essentially x to the -1, right? What's the antiderivative of 1 over x? What's a function whose derivative is 1 over x?
X to the power.
Well, that is what 1 over x is. But we know a function whose derivative is 1 over x. That's the natural log of x. So the antiderivative of 1 over x is and I'll leave this absolute value on here. We can talk about it more when we have more time to get into it, but the antiderivative is the natural log of the absolute value of x. How about h of x equals sine of x? What would capital H be? Okay, here's some negative cosine of x. Are we sure about negative cosine of x plus c? Is that just the derivative? What's the derivative of sine of x? Plus c, right? No. Not when you do the root. So yeah, but the antiderivative of sine of x is negative cosine. If you ever have any doubt, let's do it right now. What's the derivative of negative cosine of x? Yeah, let's go. So derivative of cosine is negative sine, right? Negative sine. Should get you back to where you want to go. Any questions about that? Do we have time for this one, or should I not? Yeah, let's go ahead and stop here. So I will put a due date up for section 4.5. I owe you a solution to that one that I got stuck on it up here, but yeah, we'll do more with antiderivatives. And on Wednesday, one thing I want to remind you about is that the next test, the last non-final test, is 2 weeks from today, which is April 18th. All right. I will see you all on Wednesday.